All right, so here's what we're going to do first off. Rather than go through the normal boring syllabus, blah, de blah, blah, we are going to do the, we're going to do the birthday problem, and I'm just going to start a new sheet and just start it fresh and see what happens. So Mark may or may not have covered this, or I did. I don't remember last semester. If this just goes really quick, great. If it's a struggle, then, well, let's take it from there. So here's I'm not sure what to say about that. So here's what I want to do first. My pen working? Okay, here we go. So first problem is, how many minutes old is a 100-year-old person? And just let me know when you're done. How many minutes old is a 100-year-old person? Fresh here too, so I know.
100-year-old?
Minutes old is a 100-year-old person.
On their birthday, at their exact minute of birth.
Yeah. For a second, I was like, wait, is it a 101-year-old? No, you've lived for 100 years. Yeah. I think the Chinese do it differently. You're actually 1 year old on the day you're born, and so, yeah.
So you really don't have the world's oldest person.
Minutes or seconds?
Minutes, yeah. All right, done? Close enough? All right. So here's how I'm not going to dictate how you do your own mathematics, but the way I've written it out, rather than the parens and all that, I've just used this sort of table-like format to write out my numerators and denominators. It's just sort of easier for me to think about because I know almost all these problems, every single math problem boils down to addition. And, frankly, multiplication is just repetitive addition. So this is, and division is just the opposite of multiplication. So all we're looking at here is just multiplication and division. That funny little dot there just means multiplication rather than writing the x or the time sign, because a lot of times in algebra you'll use x for times, and so I try to not use the x for multiplication. Sometimes you'll see the asterisk. I don't use the asterisk for multiplication either because it means convolution in mathematics. And sometimes I don't even use the dot. In fact, all of this stuff on the left, there's no multiplication symbol. It's just implied that everything on the top is multiplied together, everything on the bottom is multiplied together, and everything that's on the bottom is divided into everything on the top. So this is the simplest way I've found to arrive at a solution. So, and then let's also get straight numbers versus units. So I'll just go ahead and highlight the numbers. There's a 60, there's a 24, there's a 365, and there's a 100. So really all we're going to do is multiply those four numbers together. Right, aren't we? Yes. There are two parallel problems going on here. One is the numbers, and the other one's keeping track of the units. And that's, I think, where your algebra skills come in, where you're like, 5x plus 5x is 10x, 5x times 2y. You're keeping track of the x's and y's, which play the same role as the units do in a problem like this. So let's take a look at the units and see how they cancel. So I'm going to cross through the hours. They cancel, top and bottom. 1 hour divided by 1 hour is 1, so there's a 1 there that's going to be there, but not have to be written. Same thing, cross through the days. Same thing, cross through the years. So I've got 6 lines, 3 on top, 3 on bottom. All 6 of those lines just end up being the number 1. That's all it is. You divide an hour by an hour, you get 1. Divide a day by a day, you get 1. A year by year, you get 1. So the only thing that survived was the minutes. So the only thing we're left for us to do is multiply the numbers together. 60 times 24 times 365. We'll just round the leap year thing, not a big deal, times 100 equals 52,560,000. Okay, so we're back over here. 52, 56. Okay, and then don't forget the units, that's in minutes. All right, so that's the easy part. Now, what I want you to do next is pretend that you've got a rich relative who's put $1 in the bank for you every minute, and so now you're 100 years old, and you got $52 million, right? Because you're a 100-year-old person. Now, when I want to compare this birthday problem to retirement problem, inheritance problem, whatever you want to call it, is our fossil fuel supply. So what I'd like you to do is tell me when you get to retire, if instead of getting dollars in your bank account, you're getting carbon bonds. Because essentially that's all these fossil fuels are. They're carbon bonds that were put there through some photosynthetic event, geological time kind of cooks them down, turns them into a ready-to-use combustible product. And here are the parameters. So you're going to need to tell me about how many years ago. So we were just working in the units of minutes for the inheritance. Now let's work in the units of years. So I want you to tell me how many years ago that carbon bank started. So take an estimate as to how old the planet is, about when you thought life started. You can look it up, Google, just guess. It's a big number. And then we're going to work under the assumption that we started with making withdrawals from that carbon bank in 1865 in Titusville, Pennsylvania, and you probably remember learning about that in 101. And here we are now, and it is 2015, and we're also going to work under the assumption that we have consumed approximately half of all fossil fuels that were deposited here in the solar bank, in the carbon bank. And now, I'm not going to get too crazy into the distributions, but let's just kind of say we started here started consuming. We're consuming as quickly as ever, right? The technologies have gotten bigger, the fracking, the deep water drilling, the open pit mining, et cetera. We're going after about as hard and fast as you could imagine, and that we're about halfway through it. And you probably remember some of those statistics from 101. That means that we're going to be out of fossil fuels when?
150 years.
Well, give me a number.
So, 2,165?
One more time?
2,165?
Yeah, 21. Yeah. Okay. So, and of course, there's like a long tail here. There's a tail over here. But we're just going to sort of focus on this one unique portion of history we're in. Okay. So this is you can think of this as your retirement. This is your retirement period in years, because this is when you're collecting from that carbon bank, right? Okay, so go back to the money problem and tell me how old you are when you retire with the money. So compare the carbon bank, however long ago that was deposited, with the carbon extraction rate, and tell me how many years or days or minutes or seconds old you are when you get to retire with that $50 million. I'll start the clock now. Let the Jeopardy music play. And then, but form little teams of two though for this one. So you guys, you can just turn around there, yeah, just and work together.
Quickly you use the money, or when you start using it?
It's kind of the same problem. Yeah, it's the same question. The question is whether how quickly you use it or when you get to start, and one of those will answer the other. Yeah.
So we get to make up our own numbers?
I think I've given you all the answers that will constrain you to a fairly definite answer. You're going to have to guess about when the carbon bank started, but that number's not going to matter that much. You'll still be about right. So make an educated guess about when how many years ago that carbon bank started, and then we'll, yeah.
I remember when carbon dioxide, I would like to be
That's 1565 too. That's extreme time, half of all.
What else we do?
Positive. So essentially, really fast, we used 3.5 years worth of oil, 150 years. And so, if that oil was the money, how long would it take us to use this money? So we're basically, there's a few ways to just find the ratio between. You know, like our
That's fine.
you could probably find like the ratio between these two, essentially, just 500 one would be. It's going to be a really kind of.
We're trying to compare it.
Tough question, the way it's posed is tricky too. No, yeah, I'm thinking both ways. It's just, you know, we've used, basically, we've used 3.5.
I know this is very size.
Yeah, so what I did to figure out is just, you know, set it up out there. It's just treat, I mean, different vegetables, different fish dips. Because you get these one, which is X. So once you inject it, 5 minutes, since we're going to time. So I set up so that, you know, these two ratios should be equivalent, right? 5 billion years is 150 years. Should be the equivalent of this much money to the X. And so once you divide that out, you get this number. So basically, this is, you know, at this point, once you simplify it, this is where it ends. So, multiple choice by right? Divide. That's what that is.
Flanagan. I have the privilege of serving as the mayor of the city of Missoula, Montana, which is the place you find yourself right now, ladies and gentlemen. This is a fantastic turnout, ladies and gentlemen. So we were actually only expecting 10 people. So the fact that you are all here is a testament to your commitment to what we're honoring here. Ladies and gentlemen, I give you the governor of the great state of Montana, the Honorable Steve Bullock.
The country for entrepreneurial activity in this state growing up, and most fitting for most. Thank you for finding those compound names.
Oh, you guys sound good.
Process anyhow.
It's gonna be kind of hard to have to go forward, so we'll be learn.
Free drink tickets, so.
At SponCon? Oh, they have, yeah, that's good. Don't wanna
Probably like lemonade.
start that too early.
They have some fruit punch.
Let's take a cooler with us. At 10 o'clock, we can sit down and drink beer and make fun of all the other teams. So we just need to hear back from Jesse. I would guess that we're gonna have team members probably right up until.
Oh, I think I might have heard from Jesse already.
Do you know the answer, perhaps?
Yeah.
Or are you just trying to get?
I know my answer. I mean, you can, if you want to try to convince me that yours is right. Oh, yeah.
All right, so you can do it,
Yeah,
so,
yeah,
Sweet.
yeah,
awesome.
yeah,
I'm golden
We don't
yeah,
even need another person unless we just need like the,
for sure.
yeah.
somebody to just.
Where's Thais though?
So
Oh,
just-
totally, good question. Okay, so let's, so yes, I do know the answer, or a answer, an approximate answer. Time will only tell though, right? We're still writing history as we speak right now. What'd you come up with? Give me a guess. Give me your optimistic and your pessimistic guess.
We count by zero.
90?
99 years old?
Okay, so let's say 90 is your optimistic, and then 99 is your pessimistic, okay? How about over here? Did you get a number?
Yeah, so I think I was still doing the question wrong, but I got the amount of time you expended it.
Okay,
We spent
that's
it at
okay,
the same
that's
time,
fine, yep,
right?
sure.
2.25 minutes?
2.25 minutes, so that's basically 99 years, 364 days, 23 hours, 57.2 minutes. Okay. That may or may not be right. Let's just, let's work through the problem and just see how we do. Okay, so really all I was asking you for is a ratio. So we had years on one side, minutes on the other. Let's just we'll put the years on the right. In almost any problem, you want to have your unknown variable on the left, right? So everything, the stuff we know is going to go on the right. And we're going to make the assumption that life started about 3 billion years ago. And we've sort of guesstimated that it will take 300 years to consume that 3 billion year old bank of carbon. So I'll put my units on the top, units on the bottom. Now, obviously, the larger of the two numbers is on the bottom, and we'll do the same thing for the right-hand side. The units are in minutes, and we determined that a 100-year-old person is about 50 million minutes old. And you might notice that I'm only using one significant digit here. I'm kind of skipping all the other ones because we don't know the answer that accurately, and there's no reason to be that accurate with this particular problem.
They
So,
might be Chinese,
what's that?
and they might be Chinese.
They might be. So let's just keep it simple. And so we're just looking for x. What does x equal? Now, you might be able just to look at this thing and say, well, gosh, well, count the zeros. Here's how I would proceed with it. I would just kind of look at this thing, cross off those two zeros, cross off these two zeros, cancel my units of years, and then what I'm looking at is this. I'm looking at 3. Actually, well, we'll take it one step at a time. Looking at 3 divided by 3, 1, 2, 3, 4, 5, 6, 7. Throw in my commas. I got rid of the years. Then I've got x divided by 50 million. 50 million minutes. And from there, hopefully by now you can see it's about it's a 10 million to 1 ratio. I guess you could write it out one more time if you wanted to. 10 million to 1 ratio equals x over 50 million minutes. And then just to be complete, we'll say that x equals 50 million minutes over 10 million. And hopefully by now it's pretty clear that 50 million divided by 10 million is 5. So I think the number you probably got, Zach, was the remainder of the time.
Yeah, we used 150.
Yeah, okay, there we go. Yeah, okay, right. So 5 minutes. We're right now in the middle. We're halfway through the 5-minute retirement party. Well, you might say, well, gosh, humans haven't been alive for 3 billion. Well, no, we haven't. But if you remember back to 101, this book was really about systems. And if you just sort of think as Earth as a living system, and the fact that we're taking the formerly living carbon bonds and pushing them through our technologies, we're more or less consuming the biomass in this large bank. So the take-home message is that, yeah, we're going through this resource 10 million times faster than it was deposited. And that's hard to argue with. And in this class, I'm also going to share with you a paper that was just published this year where I think, at least I got a new perspective on exactly what biomass is. I mean, I know, so in 102, there's a whole chapter on biomass, pretty extensive, all the different types of biomass, oils, cellulosic, woody, et cetera, et cetera. But when it comes right down to it, I mean, the fossil fuels themselves, they were biomasses. And it's a big carbon bank. I recently learned that the fracking technology, so First you go down, then you go horizontal. They've now figured out how to come up. So, just at a conference this fall, I'm like, well, at some point, you come up, and they're like, hey, look, there's like tree roots up here. So, some even fresher biomass. So, anyway, the paper that we're going to read really takes a more inclusive view of what biomass is on the planet. And even, it's funny, this summer, someone's saying, well, is that a solar car? Well, when it comes right down to it, every car is a solar car because the fossil fuels that we're burning, those bonds were put there through a photosynthetic event however many years ago. So yeah, it's a solar car, just, using really old photons. Okay, so that's a good perspective. I think good way to get started on 101 and 102. Let's get through the syllabus. I'm not going to take a heck of a lot of time on it. It's a lot like the 101 syllabus. You've been through that because in, 20 minutes or so, 15 minutes, we'll head back and put the wind turbine up, which I thought was a great experiment for 102. Well, not experiment, but task.
Different every time.
Hopefully it's not an experiment.
It's not repeatable, so.
All right, so here's the 102 syllabus. Actually, I'll take a 2-minute break since that's kind of a long. I'll try to keep the lectures or the lecture chunks to 30 minutes or less. So I'll take a break here.